Is time travel physically possible? If you were waiting next to a black hole while 100 years passed on Earth, you would have only lived 1 year. This video is not science fiction, it's real. This phenomenon, which Einstein predicted mathematically 115 years ago, has today been observationally proven. In 2020, the Nobel Prize in Physics was awarded to two astronomers who proved that time truly flows differently by observing the black hole at the center of our galaxy for 30 years. During the same period, many technologies from GPS satellites to quantum clocks use Einstein's theory in practice every single day. So, what is time? Why does it keep changing? And can we ever control it? Number, number, time is not constant. What we got wrong. Most people think of time as something universal. It flows the same way in London, New York, and on Mars. Newton said the same. Time flows absolutely and on its own. In 1905, 6 year old Albert Einstein shattered this assumption. In his special theory of relativity, he changed everything with a single statement. Time is not constant. It is shaped by speed and gravity. If you move fast, your time slows down. If you stand next to a massive object, your time slows down. This is real. A concrete example, the airplane experiment. In 1971, physicists Joseph Hafele and Richard Keating placed the world's most precise clocks, atomic clocks, on an airplane. The plane flew a 40-hour trip around the world. The result? The clock on the plane fell behind the one on the ground by 0.000000234 seconds. It sounds tiny, but when you think about it, this was the first direct experimental proof that Einstein was right. We call this time dilation. Gravity also slows time. In 1915, Einstein went one step further with his general theory of relativity. The stronger the gravity, the slower time flows. So, on Earth's surface, time passes slightly slower compared to an astronaut floating weightlessly in space. The difference may seem small, but it is measurable. And if we don't account for it, GPS stops working. We'll see that later. Number, number black holes and the limit of time. What is a black hole? Karl Schwarzschild, who solved Einstein's equations, found a remarkable result in 1916. If a star is massive enough, it can collapse into a point of infinite density. We call this a black hole. Around a black hole, there is a boundary called the event horizon. Nothing that crosses this boundary, not even light, can ever return. Time near a black hole. Einstein's equations made a clear prediction. The closer you get to a black hole, the stronger the gravity, and therefore the slower your time flows. Mathematically, at a medium distance from the black hole, while 1 year passes for you, 2 years pass on Earth, very close to the event horizon. While one day passes for you, thousands of years pass on Earth. This remained a theoretical calculation for decades. No one could directly observe a black hole. Hawking radiation. In 1974, Stephen Hawking used quantum mechanics to discover something surprising. Black holes actually slowly radiate energy outward. Just outside the event horizon, quantum fluctuations were creating particle-antiparticle pairs, one falling inward, the other escaping. This escaping radiation is called Hawking radiation. Hawking radiation has not yet been directly observed because the signal from real black holes is far too weak, but its mathematical foundation is solid and widely accepted in the physics community. Number 30 years of observation and the Nobel Prize, the monster at the heart of our galaxy. Seeing black holes directly is impossible. Light cannot escape. But in the 1990s, two astronomers independently developed a different idea. If a black hole exists, the stars around it must be orbiting at extraordinary speeds. Germany's Reinhard Genzel and America's Andrea Ghez began observing Sagittarius A, the center of our galaxy, with infrared telescopes. Infrared light was essential to cut through the dust and gas blocking the view. Over 30 years, they made thousands of observations. The findings were shocking. Stars in that region were orbiting at 20,000 kilometers per second.
A brilliant star blazes past the galactic center at unfathomable speed, leaving a blazing light trail illuminates.
The only thing that could explain this motion, an invisible object with a mass 4 million times that of the Sunday, a supermassive black hole. Proof that time changes. As observations became more precise, finer measurements became possible. When the redshift in the starlight was analyzed, a shift was seen beyond what the Doppler effect alone could explain. The reason for this extra shift, as the star approached the black hole, time slowed, and light coming from a region of slower time arrives with a stretched wavelength. This was the first direct observational proof of Einstein's general theory of particle-to-particle. Now, here is the rest of the relativity.
Laser stability is
The 2020
nominal.
Nobel Prize in Physics was awarded to
Calibrating for the
Genzel
next
and
run.
Ghez. They shared the prize with Roger Penrose.
Wait, look at the
who had
monitor.
mathematically proven that black holes
It's a
must exist.
gravitational wave.
Gravitational
We've detected
waves.
it.
They should create waves These are called gravitational waves. These waves are so small that no instrument could measure them for decades. In 2015, LIGO, Laser Interferometer Gravitational Wave Observatory, recorded a historic signal, GW150914. Two black holes had collided
happening.
1.3
They're lighting
billion
up.
light years away, and this vibration in the
Over
space-time
90.
fabric
Einstein
had
was
reached
right.
Earth. LIGO was able to measure a length
Incredible.
change 1,000
A
of the
new
diameter
era.
of a proton. To date, more than 90 gravitational wave signals have been recorded. Every single one confirmed Einstein's equations. GPS and Einstein in everyday life. Many people think relativity is an abstract theory, but the GPS in your phone every day cannot work without Einstein. The GPS system relies on more than 30 satellites orbiting Earth. Each satellite carries a precise atomic clock. The problem: these satellites are 400 kilometers up, where gravity is weaker. According to Einstein, time flows faster in weaker gravity. The calculation: satellite clocks run 45 microseconds ahead of Earth clocks every single day. If this difference is not corrected, an 11 kilometers position error accumulates every day. Within a week, GPS takes you to completely the wrong place. Banking, aviation, and logistics systems collapse. GPS engineers deliberately wrote this correction into the code. Every navigation operation uses the general theory of relativity. What Einstein wrote on paper in 1915 runs silently in the pockets of billions of people today. Quantum clocks and new measurements. Atomic clocks measure a second with 1 trillionth precision, but the next generation of optical quantum clocks are a billion times more precise than that. What is this precision good for? In a 2023 experiment, two quantum clocks were placed in the same room with only 1 meter of height difference between them. The result? The lower clock ticked measurably slower than the upper one, because being just 1 meter closer to the ground slightly increases gravity. What does this technology provide? Underground resources. Dense ore or water reservoirs locally alter gravity. With quantum clocks, these anomalies can be mapped and resources located. Pre-earthquake signals. Tensions in the Earth's crust affect gravity. Precise clocks can detect these changes in advance. Climate monitoring. Millimeter scale changes in sea level can be measured from gravitational differences. Is going back to the past really possible? Closed, time-like curves. Einstein's equations theoretically allow for an intriguing possibility. Closed, time-like curves, regions where time could loop back on itself. Mathematically, this is possible. But a problem immediately arises. The grandfather paradox. You go back in time and prevent your father from ever meeting your mother before you were born. Then you were never born, so you couldn't have gone back in time. Contradiction. Hawking's answer. In 1992, Hawking proposed the chronology protection conjecture. The universe probably protects itself from these paradoxes. Even though the equations permit it, some unknown physical mechanism may actually prevent travel to the past. This is still just a hypothesis not proven. The many-world solution. Some theoretical physicists proposed a different solution, the many worlds interpretation. When you go back in time, a new branch of the universe is created. The paradox arises in the new branch, not in your original universe. No inconsistency. This too is still speculative but mathematically consistent. Travel to the past is, as of today, physically impossible. But forward time travel, that is, aging more slowly than others, has been proven both theoretically and experimentally. What could happen in the future? Within the framework of current physics knowledge, here is what is being researched over the coming decades. Space travel and aging. On a spacecraft moving very fast or in an orbit close to a strong gravitational field, time inside flows slower than outside. This means astronauts on long interstellar journeys would age less. The technical obstacles are enormous, but it doesn't violate the laws of physics. Precise timekeeping. Quantum clocks are becoming precise enough to revolutionize gravitational mapping and navigation. Gravitational wave astronomy. LIGO and future larger detectors, such as the space-based LISA project, will be able to scan the universe with an entirely new eye space-time waves. Controlling time with a switch remains in the realm of science fiction, but we now know that time is not constant. It is measurable and calculable. Closing. 115 years ago, a young clerk asked, "What are at would happen to time if I traveled at the speed of light?" That question led to special relativity. 10 years later, the same man said, "Does gravity affect time?" That question led to general relativity. For 30 years, two astronomers patiently watched the sky. That patience led to a Nobel Prize. And today, in every navigation operation, in every GPS signal, Einstein's equations written on paper are working silently. Time is not constant. It only feels that way.